Welcome. In this video I would like to show how to make the movement of the RR1 robotic arm more smooth by using sinusoidal acceleration and deceleration for joint movements. The reason why I decided to deal with sinusoidal acceleration and deceleration is that there was some little vibration in the robot when it stops and starts. It is visible on the tip of the gripper when the robot moves. And this is because previously I used some kind of linear acceleration and deceleration, and here when the speed profile is linear, for example, it has non-zero derivation at the moment when the robot starts and stops. In other words, acceleration and deceleration when the robot starts and stops is non-zero, and it causes kind of vibration. We can eliminate this by using speed profile that has zero derivation at the time moment when the robot starts and when it stops, and such speed profile is, for example, sinusoidal, and that's why we are trying to use it. We can see here vibration on the tip of the gripper when the robot starts and stops, especially when it stops. When the elbow joint moves, the vibration is quite visible. Let me explain in detail how this sinusoidal acceleration and deceleration is implemented. This is a sinusoid, and we need to take part of sinusoid from minus half pi to half pi. That exactly corresponds to zero derivations in minus half pi and in half pi. So this is exactly what we need, and we will use this to represent speed of the robot. Of course, we will shift that so that is more suitable for us. So we will shift it to 0 point, and also we move everything so that the maximum is 1. We cannot simply put sinusoidal acceleration and deceleration into the speed profile, because usually we need the joint to travel a certain angle, and this angle, the given angle, needs to be traveled by using sinusoidal acceleration and deceleration profile. So for given angle or for given number of steps, because the robot is driven by the stepper motors, we need to calculate the time for which we need to run the sinusoidal speed profile. So first let us express the formula of the acceleration profile of the first part of the speed profile, which is half sinus x minus half pi plus 1/2. We need to integrate this part, this formula, from 0 to pi, which is half pi altogether, because this corresponds, when we use this speed profile, the number of steps or the angle traveled equals to this integration. Of course, we need also the deceleration part, so this integration appears twice there. So first accelerate, then constant speed, and then deceleration, acceleration and deceleration both using a sinusoidal speed profile. The blue part corresponds to the angle traveled or to the number of steps. Let's scale the speed profile because we need some real speed in the end, not one. Some real speed. We will denote this final speed by V, and we will scale the formula so that the final speed will be V. Time to accelerate will not be pi, but instead we will scale that to t1. So t1 will be time to accelerate, and similarly t2 will be time to decelerate. And as we have identical speed profile for acceleration and deceleration, time to decelerate t2 equals t1. The time spent at the maximum speed v will be denoted as t, and this is time for which the joint travels by constant speed v. Okay, let's scale the formula. We will multiply formula by v, so the result of the integration will be multiplied by v. Now let's calculate the area of the blue part, which corresponds to, as I said, to the angle traveled or to the total number of steps. So this is the area of the acceleration part scaled by t1 and v. The area of the flat part, which is t times v, plus the area of the deceleration part, again scaled by t2 and v. And altogether this is the total angle or the total number of steps, which is given, and from this we need to calculate t1, t2 and t. So let us simplify the expression a bit. We can eliminate pi everywhere, so we get much simpler formula. The total number of steps is the input, from which we need to calculate t1, t2 and t. V is also given, we know that, because this is our parameter given by specification of the joint. Okay, let's make some space for further calculations. I will try to keep the figure of sinusoid visible. So V is S1 will be the number of steps to reach the final speed V. And this is also a given parameter, we know this. This is given by the specification of the joint. So S1 is given, and from this we can calculate the time that will be spent to reach the speed by using the sinusoidal profile. And from this we can easily calculate that T1 is S1 divided by V times 1/2. We can see everything in the code. We can visit the code through my web page and through my GitHub and project RR1 firmware, which is firmware for the RR1 robotic arm for revision 2. And the code is quite big, but we are interested only in a small part, and the part that shows the speed profile. This code controls the rotation of motors, and the speed profile here is implemented as simple condition, and the condition has two parts. In the first part, this is acceleration, so this means when the time elapsed is less than the time needed to reach the speed. So in that case we are in the acceleration part, and if this is not the case, if we are in deceleration part, so this means that the remaining number of steps means that we are in deceleration part, then we decelerate. And some functions are called here calculation of current speed. I will show that next. Here we have calculation of current speed according to sinusoidal speed profile, and this is our expression that we had at the beginning. So sinusoidal function shifted towards 0 point and scaled by the final speed. Final speed corresponds to v in our calculations. Calculation of times in the code. So we first calculate the time to accelerate, then from this we derive the time spent on the constant speed v, and the return value is the total time, which is 2 times the time to accelerate plus the time at speed v. We can here clearly see the input parameters, the final speed v, the total number of steps or the total angle needed to travel, and the number of steps to accelerate, denoted as steps to speed, which is S1 in our calculations. Now let's go to calculate t, the time spent at constant speed v. So we need to take the total number of steps and subtract the number of steps spent at acceleration and deceleration, so which is 2 times S1, because S1, the number of steps to accelerate and the number of steps to decelerate is the same, and when we divide it by v, we get time spent at constant speed v. Let's denote some identities. T1 equals T2 and S1 equals S2. S2 is the number of steps to decelerate. Again, let's go back to code and we can see it here. This is the total steps. This is S minus 2 times S1, from which we can calculate the time spent on the constant speed of v. Let's see the results in reality. Real robot 1 is moving and the motion now is much smoother. So the improvement is quite substantial. The vibration is almost eliminated. This is important for the elbow joint when it stops, and it is almost not visible that there is any vibration, which is quite good. And of course, this sinusoidal acceleration and deceleration profile was implemented for all joints, so we can see much smoother movement across entire robot now, and the improvement is quite substantial. Thank you for watching. If you like the video, please subscribe the channel, and I'm looking forward to your comments.